So, yeah, welcome to the talk about Machinekit Multicore. So this talk I will do together with Charles. The presentation was kindly provided by Mick, and yeah, we're talking about a brief summary of what happened. Like basically, what are the changes of Machinekit Multicore branch?
Yes, hi, Charles Stankuler. I would also like to, before we get started, refer anyone who might wonder a little bit about why some of this is happening back to, I believe it's last, or maybe the 2015 meetup. I did a presentation on Real-Time 101, which was a very, very, very brief introduction to some of the things that can happen, including multi-core cache line effects and some of the reasons why the existing HAL architecture was not really appropriate for running on modern multi-core machines. So that's why we did the work in the first place. I'm just going to read this, or So on 7th February 2017, a body of work called Multicore was merged into the main Machinekit repo. This was generally work done a couple of years earlier by Michael Haberler and Mick Grant, and the overall goal was to make the Machinekit HAL layer work well and safely across modern multiple cores on today's modern CPUs, where even your cell phone has 4 or 8 cores in it, and modern PCs have lots. Again, you can go back to the Real-Time 101 presentation I gave a little bit for a little more detail. But in the legacy implementation of the Linux CNC HAL, the components, especially those that crossed the thread boundaries, things that would have components operating both at the servo thread and at the stepper thread, or the fast thread rate. That would be things like the PWM generation, step direction generator, the encoder component. Those made very specific assumptions about the threading model, how the threads executed, and would fail dismally if you were on either a multiple core computer or a single core computer that did not have exactly the right flavor of thread preempting. And the goal with multi-core was to improve the performance of that, to make it robust, to let it work with arbitrary numbers of cores across multiple different threading schemes, and provide the missing synchronization primitives and other pieces required to do that easily, and replace what is in legacy Linux CNC. Some of these things exist in legacy Linux CNC, but they've been implemented multiple times and reinvented several times. For instance, there's a sort of an implementation of ring buffers in the HAL scope component. There's another somewhat similar implementation in some of the logic between motions, real-time and non-real-time parts, but not anything that's really been reused or is reusable, and basically promoting some of that code to a first-class HAL citizen, and to an API level where components can use that to talk amongst themselves or between real-time components in user land, multiple user land components. It just becomes part of HAL, part of the library. So I think it's probably so yeah. Again, legacy HAL mostly communicated with atomic operations. So anything that happened or needed to be communicated that was more than what you could do in a 64-bit atomic operation was either dangerous or had a sort of, hand-rolled solution for that particular instance that they got implemented. There wasn't any sort of API functionality to allow supporting that. Also, atomic operations are, even on 64-bit values, are not sort of universally available. On some platforms like the ARM, if you don't expressly do an atomic transaction or request an atomic transaction, it will not be, it's not guaranteed to be atomic. And the way that the legacy HAL was referencing values was simply a pointer indirection. A HAL pin or signal or parameter was just a memory location somewhere. And all of the different components would simply access that by either reading it or writing it. And it was assumed when you read it or write it that it was atomic. But again, that's not guaranteed. Actually, in some cases, that's not even guaranteed on x86 systems, but not in a way that would have affected the Linux CNC code that much. But part of the multi-core changes was to make the access to those atomic variables via explicit methods rather than simply doing a memory read or a memory write. There would be a accessor method where you would say get HAL value or set HAL value type of a command. And then that could be abstracted into whatever is required for that particular platform, and allows more architectures to be supported appropriately. Let's see, memory barriers. Yeah, there's support for memory barriers as well. That really doesn't tie in much to what else is on this page. I'll go to the next one. So yeah, so there are, however, many instances where the amount of data that needs to be shared is more than what you can fit in a single atomic transaction. And example would be the encoder actually feeds back more than one 64-bit value, the encoder component, to the from the fast thread to the slow thread. And that's simply handled by reading it twice and seeing if both values match, which is not a particularly effective way of doing it. And there are other instances as well. As I mentioned, HAL scope. The motion communicates very large blobs of data across the real-time, non-real-time boundary. So ring buffers is a traditional way of handling this. They're lock-free, single reader, single writer queues. They don't require any form of locking or mutex or other sort of handshaking. So they're fast and they don't block. And they've been included in the multi-core HAL. They've actually been in the Machinekit HAL for a while. They are also included in the multi-core, and they got updated and changed a little in the multi-core commit. So if you do have anything that is using the existing ring buffer implementation, it probably will need to be recompiled, and it may need a very minor amount of recoding. But it's very straightforward. I've got some ring buffer components that to get it to work with multi-core, I had to change like 2 lines of code. It's pretty trivial. Oh yeah, triple buffers. The bottom there, it's talking about triple buffers. A triple buffer is sort of a mutant divergent case of a ring buffer. They're not quite exactly the same thing. A ring buffer will share all data between a writer and a reader. That's important for something like, for instance, HAL scope, where you wouldn't really want to drop a chunk of data you'd want to make sure you got all of it. Other times you're only interested in what's the absolute latest, most recent value, like for instance, a digital readout or something. What's the position in the machine right now? You don't want to have to read through the last 100 values that accrued while you were running off on your slow thread to get to the current state of the machine. So the mechanism that's used there is it's called a triple buffer. There's basically a read buffer, a write buffer, and a scratch buffer. And the details of how that works are kind of immaterial, but the net result is that it works very much like a ring buffer in that both the reader and the writer are able to access that without using any form of mutex or locking or other synchronization primitives. So it's fast and it's non-blocking, and the reader always gets the most recent value, and the writer always has a new empty buffer that it can write to. And essentially the writer ping-pongs back and forth between the write buffer and the scratch buffer, and then when the reader wants a new value, it atomically grabs the most recently written buffer and flips the read buffer to the existing read buffer to become the scratch buffer. So
wherever possible, the API changes are kept under the skin. And code that worked previously should also work, still work. And there were a few differences, and also during the merge there were a few things that emerged that maybe changes, for example, in protobuf and so on, that have not been tracked back in the multicore branch, because multicore was happening a lot earlier than a lot of the, for example, machine talk changes that were implemented. So things a little bit got out of sync, and so we had to do a few reiterations for a few things afterwards after the change.
But I believe at this point there was definitely a time immediately after the multi-core merge, some things would not compile and would be broken. But at this point, all existing legacy HAL code should work as is, unless it uses one of two or possibly three of the ring buffer functions, in which case you'd have to tweak it. But I believe everything else should basically, if you had a HAL component previously, it would need to be recompiled because the headers and binary things have changed. But you other than recompiling it, the code should totally work as is. So. HAL objects. So this is one of the things that changed a lot. And previously, the way HAL memory was allocated and used for objects, there were memory regions for HAL names, memory regions for the signals, and now sort of everything related to a HAL object is kind of grouped together. So rather than putting all the names in one place and all the signal values in another place, that was done intentionally to pack the HAL signals, which would be changing all the time, into as small a memory region as possible so that it would optimize what was in the cache. But going back to the Real-Time 101 presentation I gave, that actually causes horrible performance problems on a multi-core processor, where if you have two cores that are trying to write to different addresses in the same cache line, they get into a fight basically between which core owns the most recent version of that data. And that is to the extent that memory access is drastically slower than cache access, the cache arbitration logic is drastically slower even than memory accesses, and it causes your super fast processors to come to a grinding and screeching halt, and performance drops off by factors of several thousand. So by grouping a HAL object with all of its data and metadata together, that essentially pushes the signal memory locations for different writable HAL signals and parameters out of the same cache line. Just sort of, it's a natural occurrence of this, the way that everything's grouped. So that's actually quite beneficial when you're dealing with multiple core machines, and also when you're dealing with more modern machines that have drastically larger caches than existed in the days when the HAL layer of Linux CNC was originally being written. And let's see, callbacks, HAL command.
So internally, like there previously before the multicore branch, all sorts of like update functions that iterate over HAL structures use their own loop basically, and this has been replaced by a single loop called HAL-G for each. So this is a recursive iteration. So basically this routine can be called with a callback, and inside the callback, like basically it works with the HAL object, so it can work for any sort of object. Like let's say it's a normal HAL component, it's a remote component, or something else. And this way, things can be handled in one position in the code, which is a lot beneficial. There was a lot of repetitive and redundant code in there that has been removed. Also, the handling of the mutexes and so on, therefore, gets a little bit simpler. Yeah.
Okay. Did you have much with that?
Yeah, I mean, I've not myself not experienced it yet, but basically with HAL instances, there were quite a few problems because an HAL instance is still was still a normal, let's say, a component, but the parameters like could cause problems. Let's say, for example, you're passing a string as an instance parameter. Then previously this could lead to memory access problems because the first use of the parameter defined the allocated memory, and if there is, for example, a string passed afterwards that was bigger, then it would cause out of bounds accesses basically because the previous allocation was smaller. So this has been fixed now, and therefore it's now possible to use like more complex or like string parameters also for HAL instances basically.
Right, and this goes back to one of the major differences between the Machinekit HAL and Linux CNC HAL. If you are working with HAL, which is dynamic, you can create nets, you can wire pins to other, inputs to outputs dynamically, change parameters. But what you can't do in Linux CNC HAL is if you load an AND component, an AND2 for instance, and then you decide when you load it, you have to tell it how many components there should be. So you're like, oh, I just need one. Well, then you're playing with HAL a little bit, and you're like, oh, I really need another AND component. Well, you can't. You can't add that. You have to basically start over again because you can't reload the component. In the Machinekit HAL, you can load a new instance of that component. The instantiable components, you can say, I want a new AND component. It's like, okay, here you go. And then later on, you're like, oh, I need another one. So you just say, oh, I need a new instance of an AND component. And it's like, oh, okay. And that's allowed. The problem was with how some of the parameters were being passed to those when the module gets instantiated, and that goes all the way back to the original Linux CNC and the HAL layer, where all of the HAL components were actually not userland code, but actually ran in kernel space. And they were loaded as kernel modules, which is why you can't load it more than once. You can't load a kernel module more than once. You have to load it, give it its parameters, and then be done with it. Since we're in user space, that doesn't apply, and we can reload the components. But if there's a variable number or length or amount of argument data, this is now fixed. Before that was somewhat broken. So it would work in a simple instance where you're loading an and you might have to pass it an integer value or something. But if you're loading multiple things like a host mode 2, where you've got some big long command line, lots of gobbledygook, it could have been broken. But not a lot of people were doing that. But it's fixed now.
Yeah, that's basically what we have been talking about. Yeah, it's an example for instantiation of a component with a lot of big string commands, basically.
Okay, so version 2 components, the existing HAL components work as is. And they continue to access the HAL pin and parameter data as raw pointers that they simply read or write. And again, this works okay generally most of the time, but isn't necessarily ideal, and certainly is not ideal across all platforms. And what the version 2 components do is replace the raw accessing of a memory location by via pointer with the get and set functions that are provided by HAL. So it's a far safer thing to do. Also, a lot of people, if you're not careful, it can be tricky to write safe real-time code, because there are several instances in the legacy Linux CNC code base where a value is read from a HAL pin, and it's assumed that the value does not change between those readings. It's simply used as a variable. So you might need to access the value of that pin more than once in your code. That's fairly standard. However, in a real-time environment, you should properly read that once and then use that cached value, because by the time you read it the next time, something like the faster running encoder thread may have changed that value underneath you, and that can cause problems. That's one of the reasons why the Linux CNC legacy HAL code base is particularly sensitive to running on a single core and with a specific type of thread preemption. And if you change that assumption, several pieces of the code break. So more correct is to simply read it once and use that value in any subsequent calculations. Better is the version 2 method here, where rather than reading the raw memory location, you ask the HAL layer API to give you the value of that specific thing that you want. At which point the accessing function and whatever real-time or memory fence or other platform-specific instructions might be required to guarantee that that particular value is current and up to date, and the specific value that you want can be hidden from the application layer, which doesn't have to worry about it and just gets the value or sets the value and doesn't have to worry about the details.
Yeah, and instead of the functions for updating the values, they are also now in the components accessor macros, which are especially useful when you're dealing with, let's say, increments and decrements of values, for example. Yeah, because it saves a little bit to write, and also it's using the accessor macros, it's a little bit more complicated to write, let's say, increase by 1 or increase by a certain amount, for example.
Right, but so there's a standard macro header file you can include. I think it's now included by default.
I think so.
Yeah, that'll allow some simple common access patterns to be done, so the code doesn't get ugly or get too bloated just because you're using the accessor functions. Helps keep it clean and readable.
Yeah, that's some of the work Mick is currently working on. So basically, the current launcher, like the user interface that is started when you type the Machinekit command is where you can select the configuration, is currently based on by GTK. And now the idea is to replace it also with a Qt user interface. And the user interface can, for example, can also use the for each loop, for example, to iterate over all the HAL objects, and then it enables searching and also display of more specific values. Let's like visible here. Like basically, you can access like all pins and so on. So it's basically provides function to view all the whole HAL configuration, the running HAL instance, and access all the values, and provides an easy way user interface for doing that. Yeah, and for further information, please take a look at the Machinekit documentation about instacomp, especially if you're looking for version 1 and version 2 components. And there is also a new tutorial document which is explaining the difference with the debounce component, and explaining also how to write the debounce component as an inst component instead of a normal component. Yeah, and thank you very much for your attention. And like, are there any questions?
Is anybody writing HAL components? Yes.
Yep.
Yeah. So. As stated, the existing method of writing them still works fine. Accessing the pins and parameters via a pointer dereference. But things are moving towards the accessor methods. And you do just sort of want to be careful with the pointer dereferences and how you code things. The legacy Linux CNC HAL does make it very easy to write hard real-time components. You can write a few lines of Z code, and using the comp command, it's almost deceptively easy to make something that works properly in real time. But it's still deceptively easy to shoot yourself in the foot, which is very easy to do in real time. So, you know, beyond simply the like, well, I just did a printf to put some debugging info out to the screen. Why did my real-time performance just die? You know, there's also there's many more subtle ways that you can trip yourself up. So one of the goals with the version 2 is to make it easier to wrap some of those things that can be tricky to do right, and get them offloaded into the HAL library where we can code them correctly and make sure that they're properly implemented, and then people don't have to worry about side effects. So especially when you get on systems like the ARM and some of the other systems that have loose memory semantics, on an x86, you're pretty much guaranteed that all the reads and writes to memory happen in the order that the CPU executed them in, and that your code was generating them in. On the ARM and several other systems as well, it's a lot more sort of loosey-goosey, and it's whatever bus bandwidth happens to be like, and whatever the cores happen to feel like they want to do, and your reads may get promoted ahead of things. Anyway, there's memory barriers and all sorts of fun stuff that needs to get implemented that to make sure all that stuff happens. And if you use the accessor methods, then that helps the HAL layer do that for you, and you have less to worry about yourself. So
Yeah, and it's also like very good to use the inscomp wherever possible, because it makes like writing, especially Python HAL configurations, a lot easier. Like you can just use let's say a Python loop to create new components instead of like creating them before you like at the beginning of your configuration. So if you have a bigger configuration, then that's like making things a lot clearer and easier to read.
Like an AND gate would be very trivial, but like the PID command, PID component. If you need one of those per axis, or maybe you've got some stepper axes and some servo axes, and you need a PID component for each servo. You don't have to go through the HAL file and the whole thing and figure out how many PID components you need before you start. You can just start and say, I need a new PID component. And every time you instantiate a new axis, it's like, I need another one. And then when you go from your 3-axis machine or 4-axis machine to 6 or 7, it doesn't matter. You just change a couple of numbers, but you don't have to it doesn't become nearly so complicated. So, and that's one of the things. The Python stuff is, I think, a little easier to maintain long term if you can start off that way. But like I said, most of our example configurations are still the old legacy HAL file format. But I'd like to see that changing. I'd like to see more of the Python stuff get integrated in as the example configurations. So certainly, if any of you have done any, please provide those, and we'll throw them into the repo as examples of here's the modern way to do it. So, any other questions? Yeah.
Let's look if there's something on the here.
Nope. Okay. All right. Well, thank you.
Did you discover any of these in the wild while you were working on things, or did you just know that they were going
Any what?
Conflicts as of
with the Linux CNC stuff, or
the side effects of the multi-core things with multiple readers and writers apart? And
yeah, absolutely. If you take the legacy Linux CNC HAL and you change any of sort of its baseline assumptions, there are several things that break. I can point you to numerous.
I was just curious if you were working on something in particular and it hit you over the head.
Not so much, no. But it's very easy to break it and show where it's broken if you start running some test cases. And some of the things Michael did a lot more of that work than I did. A lot of the things that cropped up were some of the runtime tests where it goes through and it does its little test of HAL at the if you ask it to. Those will break in many different, sometimes semi-randomly in different ways. If you change the threading stuff, it was happening. I think in part it first started cropping up when we were doing run tests on like virtual machines that weren't running real-time code and was just running it as POSIX, and basically in simulation mode. Then it's like the real-time stuff would be okay, but the simulation stuff was failing, and it's because of the difference between the sort of user mode POSIX threading and what was happening, and if you were actually running on a hard real-time kernel with RTAI. And then several other things, just code examination. The encoder stuff would sort of probably work okay most of the time, but it's just sort of demonstrably by inspection just sort of wrong if certain base assumptions are not met.
I assume the user space real time does not suffer on x86 is okay.
The preempt RT.
Mm-hmm.
I wouldn't know. I haven't gone through the code that they've changed. They're not using the preempt RT. They're not using the same changes to the RTAI layer that we made. They had to reinvent it. So I don't know. but there are several instances where generally it was the encoder and the step-gen components were the most problematic from the threading mechanism. They made very brash assumptions about the operating frequency and expectations of the base thread and the servo thread. And it was assumed that the servo thread could never run if the base thread was running. So the base thread basically had an implicit mutex that it always owned. And if you're multi-core or you don't run a specific threading mechanism where the faster thread always interrupts and never lets the slower thread execute, then that assumption is invalid and the code basically doesn't work anymore.
But if you're not running a base thread, not an issue.
If you're not running a base thread, you're not using the encoder component or a step-gen component, it's not a problem. And most of the things generally were thread interaction. So if you're not running more than one thread, you don't have a thread interaction problem. So yeah. So you wouldn't have you're sort of implicitly running another thread if you're using the hardware, but the driver's already set up to deal with that. So because the hardware's out there running in the background and doing its thing, but the driver deals with it. It was the communication across the base thread and the servo thread. There are also a few places where, again, it was like reading values in the base thread more than once. But if you don't have a base thread updating that, the servo thread, doesn't care because there's no, it's the cross thread stuff that was problematic. So they are doing that between user land and real time. But I believe that's another one of those, that boundary is crossed multiple places in Linux CNC. And the code to do that has been cobbled together and reinvented multiple times in multiple places in Linux CNC. But in general, I believe it probably is, it's probably no worse or better in the preempt than it was in the RTAI, and I wouldn't think that would have a lot to do with it. So, because in general, I don't know if they're making this. I don't think they're making the same kind of assumptions that they were between the base and servo, because both the base and the servo thread were real time. The user and real time thread have always been. This was a special RTAI thing, and this is just some generic user code. So, but I don't know. And those have historically also been running on different. They will intentionally run the real time stuff on one core and lock it to a core, and the user mode stuff is running happily on some other core, and everything's okay. So I think they're all right there.
Great.
So. This would affect if you're running real time on more than one core or you're running more than one thread. So, long answer to it. More than you wanted to know, probably. Yeah, don't get Charles talking about real time.
It takes some real time.
Yeah.
It's complicated.
Well, you could tell us about your crafty invention here.